Alrighty, folks. So moving into lesson 4 here for unit 1. Like I said, we're now kind of moving into sort of the second topic of unit 1. Of course, it's all, fairly closely related and uses similar ideas. But now we're going to look at transforming functions. We've been performing operations with them, composing them, taking their inverses, right? Doing things that have combined functions in many ways. But what we're going to start to look at here is just taking a function and transforming it, something you have done in previous math courses, particularly Math 20. You looked at transforming quadratic functions and their graphs and their equations, okay? We're going to take that in Math 30 now. All we're going to do is go a little more general with it. Instead of just doing it with quadratic functions, we're going to expand and be able to do it with any type of function. Okay, and we're also going to add more types of transformations that we can do than what we had in our toolkit in Math 20. So as always, there's the big ideas. You can kind of use those to check in with yourself for the big takeaways, the key skills to come away from this lesson with. So let's get into it. Like I said, in Math 20-1, we explored transformations mostly in the context of quadratic functions, especially when we looked at their equations, you might recall, in vertex form. That was this one. Y equals a times x minus p squared plus q. Okay, does that ring any bells from Math 20? One of those transformations that we looked at were translations, which essentially they slide the graph vertically or horizontally without changing its shape. So we really do, we just take it and we move it up or we move it down or we move it sideways, okay? But we're not going to be stretching it to make it like taller or wider or anything like that. We really are just moving it around for a translation. Transformations in general, that's what they do. They take a graph and they transform it. So for a translation, that's like a slide or a shift, right? We just move it around. That's how we change the graph. So recall that when the equation is written in this form, this vertex form here, right? The reason we call it vertex form is that actually just by looking at it, we can pick out where the vertex of the parabola would be. And again, recall the vertex of a parabola is the point where it changes direction on the y-axis there. It's where you'll find a min or a max for the y value, right? These are all mins, but of course if a parabola opened downwards, we would see its max there at its vertex, okay? So when we write it in that form, we can actually, just by looking at the equation, we can pick out the coordinates of the vertex. They're going to be at P, Q. So whatever we see here and whatever we see here, that will be the coordinates of the vertex. And therefore, by changing those parameters P and Q, we're moving the vertex horizontally, right? That's actually why we were so sure that the vertex would be at P and Q. Because if we just look at y equals x squared, well, we know that it has its vertex at 0, 0, right? When x is 0, y is 0. As x gets larger in the positive or negative direction, y is just going to get larger, right? 1 squared is bigger than 0 squared. 2 squared is bigger than 1 squared, right? So it just goes up like this. And same thing in the negative direction. Negative 1 squared is 1. Negative 2 squared is 4. Negative 3 squared is 9, etc. Okay, so our vertex is going to be at 0, 0. And these P and the Q, okay, are going to be our horizontal translation and our vertical translation respectively, right? That's why we can be so sure that the vertex will be at PQ, because P is going to slide it left or right. Left if P is positive, right if P is negative. Okay, so starting from an x coordinate of 0, if we slide it, P units right, the new x coordinate is now P, right? If P is 5, it's going to get slid right by 5, and now the x coordinate's at 5. Q is going to slide it up or down, translate it vertically up or down, okay? And again, the y coordinate starting from 0. So if I slide it 5 units up, the new y coordinate would be 5. If I slide it 5 units down, the new y coordinate would be negative 5, right? So it's the fact that these can be thought of as transformations to the graph of y equals x squared that allows us to be so sure in the first place that that's where the vertex will be. So here's let's run through some quick examples. Go back to Math 20 for a little bit just to remind ourselves of the effect of P and Q on the graph of a quadratic function, okay? So if we're dealing with something like f of x equals a times x minus p all squared plus q. What are we looking at, and what will we see? Okay, so as we work with more and more transformations, folks, we're going to often kind of have like a base graph that we compare back to, meaning like the simplest version of what we're dealing with. What's the simplest version of a quadratic equation? Just y equals x squared, right? Doesn't get much simpler than that. It's not being multiplied by anything. We're not subtracting or adding anything. So often we think of these transformations as transformations to like the base version of a graph. In this course, we're going to transform lots of different functions. Y equals root x, y equals, 2 to the power of x. We're often going to use that base graph to compare back to think about, oh, this is like the graph of, in this case, y equals x squared, but it's been translated 2 units down. Or this is like the graph of y equals x squared, but it's been translated 1 unit left, okay? That's the idea here. So that's what we're being asked to do. Think about each of these equations and their associated graphs as they could be thought of as translations to y equals x squared. So y equals x squared, the translations to y equals x squared, obviously none, right? We haven't performed any translations here, none, right? Our p is 0. Our q is 0. You can see in the equation, if we look at this as y equals a times x minus p squared plus q, how do I get the equation to be y equals x squared? Well, p would need to be 0, q would need to be 0. It just hasn't been translated, okay? Moving on to this one, though, y equals x squared minus 2. Well, this we can think of, look what's happened. By putting a negative 2 in q's place, right, instead of just y equals x squared, it's now y equals x squared minus 2. It's been translated, shifted 2 units downward, right? The vertex was here, now it's there. Of course, we can do this for any point. It doesn't need to be the vertex, but the vertex is a nice, easy one to see, okay? So a vertical translation 2 units down, right? Our p here, our p is 0. P equals 0, and q equals negative 2. Okay. Looking at this one here, y equals x plus 1. Now, this often throws students off. Remember, it's x minus p squared. So we don't have x minus 1, right? P, be careful, p is not 1. If p were 1, this should be written as x minus 1 squared. But it's not, it's x plus 1. So what does that mean for our p? What's the value of p? Well, if we did x minus p, okay, if we did x minus p, and that ended up being x plus 1, well, that's only really possible if p were actually negative 1, right? Again, if I'm just looking at, we'll make a 1 and we'll make q 0 just to focus in. If I did x minus negative 1 squared, right? That would be how I would get an x plus 1 squared happening in my equation. So p is not 1 here, p is negative 1. And that is why it's getting shifted 1 to the, not right, 1 to the left. Our p is actually negative 1. So this is a horizontal translation. 2 units left. Our p here is negative 1. Our q is 0. It hasn't been shifted up or down, right? We could, if you wanted to add in the 0 there, right? No shift vertically. No translation vertically. Here's one that's got both happening. Can you pick out p and q, right? Always compare, right? We got x minus p squared. So what's my p? What's my p? It's 3, positive 3. Okay, p is positive 3. What's q? Positive 2. Q is positive 2. Okay, and we can see that the vertex has been translated from horizontally from 0 as the x coordinate to, sure enough, 3 as the x coordinate. So we've got, I'm just going to write HT for horizontal translation. Horizontal translation, 3 units right. Well, that makes sense because our P was positive 3, okay? And a vertical translation, 2 units up. Again, kind of makes sense because Q was positive 2, right? Sure enough, it went from having a y coordinate of 0 to a y coordinate of positive 2 when we compare back to y equals x squared. So that is a reminder of vertex form for a parabola, because that's a really good entry point for us to understand what we're about to do. What we just did with those quadratic functions, which is really what you did with them in Math 20, we're going to now just take that and make it general. We're going to actually be able to do this to any type of function as we move forward here, right? And there's honestly not much else to it. It's just about recognizing those parameters, P and Q. We're actually going to give them different names in Math 30. We're going to call them H and K eventually to make things, so we don't get it mixed up, I guess, is probably the logic there with the specific P and Q that tell us the vertex of a parabola, okay? So if it throws you off a little bit, that again, and it does throw students off a little bit at first, that it's almost like the opposite thing is happening, because I get it, it feels like P is negative here, but remember, it's X minus P, right? If that's strange to you, let me convince you, hopefully, that it shouldn't be, right? Because the Q, I think anyway, makes some sense, right? If I have, y equals, I'm just going to put in numbers to make it a little bit easier to think about. If y equals x plus 1 squared, and I put in a Q of plus 2, let's say, right? We can see that, okay, what's this doing? If, we compare it to y equals x plus 1 squared, right? It's like y equals x plus 1 squared, except then we're adding 2 to every single y value. Well, what's going to happen if we add 2 to every single y value? They're now going to be 2 higher on the y-axis. In other words, it's all going to have been shifted up by 2, right? If I instead made that a minus 2, it makes sense that when that is negative, it shifts it down by 2. Because again, it looks exactly like the graph of y equals x plus 1 squared, right? But look what we're doing to each y value. Remember, the equation just tells us every point on the graph where the y is equal to the x value plus 1 squared minus 2, right? So it's going to look like y equals x plus 1 squared, except I'm subtracting 2 from each y value. What is that going to do to the y values? It's going to move them down by 2, right? If the y value used to be 0, now it's at negative 2. If it used to be at negative 5, now it's at negative 7. Every y value has now been 2 subtracted from it and moved down. Hopefully the Q part is fairly intuitive, but what throws students off is then why is it different for x? And it just comes from the fact that x is not actually isolated in this equation, right? If I were to say, okay, what did x, let's just make it a little simpler here. Let's do y equals x minus 1 squared, right? Why is that going to move the graph right by 1? Because it kind of feels like we're subtracting 1 from x, right? But we know that actually means p is positive 1, and therefore we're going to move it 1 to the right. Now, why is that the case? Well, again, because y is not isolated. So if we were to take this, if we were to compare, we've got y equals x squared, right? So if I square rooted both sides to figure out what is x equal to, x is just equal to plus or minus the square root of y, right? Okay, x is just plus or minus the square root of y for y equals x squared. But what if I change y equals x squared into y equals x minus 1 squared? What does that do to our x's? Well, to answer that question, we'd need to figure out what is x equal to now, right? And it's not isolated right now. So if I square root both sides, I'll have plus minus y equals, square rooting is just going to cancel out the x there. Whoops, sorry, plus minus square root of y equals to x minus 1. And look at this. This is the answer to our question, folks. If I want to get x by itself, let me add 1 to both sides. And look at this. Now x equals plus minus the square root of y plus 1. So it comes from the fact that if we wanted to isolate x, we don't actually have to do this, but it lets us accept why this feels a little bit backwards at first and understand why it's not actually backwards, right? Because look, x used to be, for y equals x squared, x just equaled The square root of y, right? Now what does x equal? The square root of y plus 1. Because by subtracting the 1 here, if I really wanted to figure out what effect that had on x, I'd end up doing the inverse operation. I'd add that 1 to both sides. And if I add 1 to every x, which way does it move? Well, again, if it used to be at an x of -5, I add 1, now it's at an x of -4. So we're going to see this over and over again for parts of our equation where we're doing transformations to the x value. It's going to feel a little backwards at first, but again, that's just because the x is not isolated. If I'm doing an x minus p, right, really what that means I'm doing is I'm adding that p to both sides. Okay, if I wanted to figure out what happened to x. Again, we don't actually need to go through the process of isolating x, but this is hopefully getting towards convincing you that it makes sense that when we have, x plus 1, our p is really negative and we're moving it to the left, right? Eventually, what would I have to do if I wanted to isolate x? I would subtract 1 from both sides. So x used to be equal to plus minus root y. Now it will be equal to plus minus root y minus 1, and that's why it's shifted 1 left here. Okay, we'll continue to think about that as we go. But there we go. That's us dipping our toes back into the idea of transformations and using the entry point of, hey, we've done this before. We did it in Math 20 with parabolas and quadratic functions. Now we're just going to extend it, okay? So in general, transformations of graphs, what are they? Transformation of a function alters the equation, and therefore any combination of the location, the shape, and the orientation of the graph. We'll look at transformations that alter all of those as we go. The new graph that's created by a transformation, we can call that the image graph. We often say the original graph and the image graph, okay? Because it's the image of the new one, right? We've messed around with it and made something that came from it but is now different, okay? Each original point, P, X, Y, all that P is saying, it's just saying the name of this point. We could call it the point P, and it has coordinates X and Y, okay? Corresponds to a new point, what we call an image point. P, we call that prime in math, that little apostrophe, we call it a prime. So P prime, right? A new point, X, Y, and we call that an image point. So all of the transformations we're going to look at, folks, what they do is they take every point on the graph and they do something to it. Maybe they move it around, like with translations. Maybe they, move it around, but by multiplying with like a stretch. Or maybe they flip it across a line, like with a reflection. Okay, we're going to start out with translations here, but big picture, that is what all transformations do. They alter each individual point individually, and therefore, if they do that, obviously that's going to change the entire graph in some way. Okay, so first one up, translations. We'll talk about translations. One type of transformation is called a translation. These are, shifts, slides, you sometimes hear them called, but the proper term is a translation. So a vertical translation slides the graph of a function up or down, right? Up or down. It's going to do this, vertical, up or down. A horizontal translation slides the graph of a function left or right. I'm actually going to change my colors here just because I know how I color code later in this lesson. Left or right, horizontal. Okay. Now a translation will change, like we said, the location of a graph, but not its shape, size, or orientation. It's really just sliding around, right? I might take y equals x squared and, move it up here, trying to draw it as similar as possible. But what I'm not doing is turning it into something like this, where it's a much narrower parabola, or like this, where it's a much wider parabola, or like this, where it's now a parabola that opens down, right? All I'm doing is taking it from one spot and putting it in another. That is a translation, shifting it, sliding it. So let's look at this example here. Just going to ask us to jump right in and translate this function. So the partial graph of y equals f of x is shown. Draw the image graph when y equals f of x is translated 3 units up and 2 units left. Okay, so again, all this does is take every single point and add or subtract something to its x-coordinate. In this case, it's going to subtract 2 from its x-coordinates, right, to move it 2 units left. And then it's going to add something, in this case 3, it's going to add 3 to its y coordinates to move it, well, 3 units upwards. So that's what we're doing here. That's what a translation is going to do. So we can take each individual point and we can just perform those transformations. So it doesn't matter the order here. I'm going to take that point that started out at 0, 0. Let me slide it, translate it 3 units up, and then 2 units left. That new point is now going to be right there. Right? That's the new vertex of this. Looks like an absolute value function, right? What did I do? I moved it 3 up, 2 left. Okay, there's a new point, what we would call an image point. Okay, if we take a look at, this one, we're going to do the same thing. 3 up, 2 left. Again, if you did 2 left, 3 up, you'd get to the same place. You can check for yourself if you don't believe me. Right, there we go. There's that image point. Okay, deleting my arrows after, otherwise it would get pretty crowded. What about this one, right? What about here? We could go 3 up, 1, 2, 3 up, 2 left, 1, 2 left, and there will be that image point, right? And already we know we're not changing the shape of it. We're not stretching this graph. We're just sliding it around, translating, okay? That's going to look something like that. That will be our new graph, right? We've just taken it, shifted it up, and moved it over to the left by 2. And there we go. That is a vertical translation of 3 units upwards and a horizontal translation of 2 units to the left. Obviously, it kind of looks smaller now, but that's just because you can't see as much of it, right? It doesn't fit as much on the graph anymore because it cuts off here. It's still, if we could see more of it, it would still be extending like that. And now it says the point 4, 8 does lie on the original graph. It just isn't visible in this selected portion. Where would you predict the point that was originally at 4, 8 to now be located on the image graph? Interesting question. So we just did it visually by, saying slide this up 3, slide it left 2. Now it's saying, what about a point you can't see? Could we still figure out where that would end up, right? We can't actually see the point 4, 8. It's just too high. It's not that it's not on the graph. It's just obviously we have to cut the graph off somewhere. And then this one doesn't show us that point. But hang on a sec. If we translate it 3 units upwards, what does that do to the y coordinate? What does that do to the y coordinate? Well, it adds 3 to it, right? 3 units up adds 3 to y coordinate. So where did it used to be? 8. Where's it going to be now? What's its new y coordinate? 11. Right? So now that point will be, the image point will be at 11 for its y coordinate. How do you think, see if you can, pause the video maybe and think about it. How do you think we're going to find the x coordinate if we shifted everything 2 units to the left? Okay, well, again, if the x coordinate was 4, we've shifted it 2 to the left, we can kind of see that it would be at 2, right? This is going to subtract. 2 units left is going to subtract 2 from the x coordinate. So, like we said, if it was at 4, it's now at 2. So where is the image point? Where is the image point? It's going to be at 2, 11. There we go. That's where that image point will be without even having to graph it. So just looking again here in Desmos really quick again. Typically, if you need to graph something with technology, I would recommend getting used to your calculator, but the nice thing about Desmos is it lets me do sliders like this so I can have good visuals, okay? I know all these like equations and parameters don't quite mean much to you yet. They will after this lesson, but I just wanted to show you, right? Here is the horizontal translation, okay? It's just sliding it. Notice it's not changing the shape. The vertical translation, notice it's not changing the shape. It's just moving it around, okay? So I can tell you that a translation of 3 units up means that this parameter is positive 3, okay? Positive 3, it's kind of hard to get it right on. And a horizontal translation of 2 units left means that this parameter is negative 2. So I didn't quite get it exactly right there, but okay, I'm not going to. But we can see, right? That's a lot like what we graphed, right? And look, the point that was at 4, 8, there it is, right? There it is on the original graph. Look where it is now, 2, 11. It's a little bit off because I can't quite get that K there to be exactly 3. But see what I mean, right? It got shifted. If we look at this point, trace it over 2 units to the left, 2 units to the left, and then 3 units up, and it's about where we predicted it would be. Cool, huh? Okay, so let's get into how we can kind of show these, okay? What we have here is something we're going to use a lot. You will find it's going to look a little different than this because right now we're just focusing on translations, okay? We're going to add as we go. We're going to build this up and add in stretches and reflections too, okay? So you'll see on your formula sheet something that kind of looks like this, but it has a little bit more going on. So we'll meet those parameters as we go, okay? So this is what we call function notation. Now this one again, this just describes translations that could happen. Transformations, what this function notation is they literally are telling you, it's instructions on what do you need to do to the original equation in order to get the equation of the transformed function. So if we know how to read it and know how to look at it, we know what these parameters are telling us to do to the graph, right? Notice how similar this looks to vertex form for a quadratic function, that a times x minus p squared plus q. Guess what? Vertex form is actually the general function notation for how to transform a parabola, how to transform a quadratic function. So like I said, we're just taking that and we're going to make it more general so that we can transform any function. That's what we're doing in Math 30 now, okay? So transformations can be described using function notation. That's what this is. It's just a description. It's a set of instructions on what to do to the original function, y equals f of x, in order to get the transformed function, okay, which is going to look something like this if all we did was translate it. It's very common and very practical because it's so general, right? This is just saying for any function f of x, if you change it in these ways, you will have graphed a transformed function, a translated function. It can be applied to any function. And once we know how to read it, which is what we're going to work on here today and tomorrow, well, in this lesson and the next lesson, okay, one is learning how to read it. It literally does. It just acts like instructions for how we could alter the original equation y equals f of x to obtain the equation of the transformed function. So we're going to build that up as we go. So notice, this is just saying if you want to translate a function, again, keep in mind the base, like the original function is just y equals f of x. If we want to transform f of x, this is telling us what we need to do. It's saying rewrite it so that instead of as a function of x, it's as a function of x minus h, right? So this literally means in the original equation, instead of having an x, wherever you used to see an x, you're going to have an x minus h, right? That's why to translate y equals x squared 1 unit to the right, instead of x squared, we would have x minus 1 squared, okay? That would translate that parabola 1 unit to the right, okay? And then we will add k to the entire equation. That will move it up or down by k units, depending on whether k is positive or negative. So again, if I had, y equals x squared, I wanted to translate it 1 unit right, let's say 1 horizontal translation 1 right, vertical translation 2 up. These are instructions on how to do that. It says replace x in the original function with x minus h. H is our horizontal translation. You're used to calling it P for parabolas and quadratic functions. We're going to call it H just to be more general with it. Okay, don't ask me why, but we swap it out for an H. That's going to translate it left or right by H units. So to translate it 1 unit right, like this says, replace x with x minus h. So a horizontal translation of 1 unit right means h is 1. So I would rewrite this as y equals x minus 1 squared. And that is, if this is f of x, this is f of x minus 1, right? I've replaced x with x minus 1. My input now is x minus 1. And then what does it say to do with f of x minus h? Add k. So if I want to vertically translate it 2 units up, that just means my k is 2. I want to slide it up. I want to add 2 to every y value so that it's 2 units higher, right? And there we go. Look at that. That's just a parabola. That's what we did in Math 20 with parabolas when we wanted to translate them, right? 1 unit right, 2 units up, okay? So we're going to build that up as we go, but I want to introduce the core ideas there now, right? So k is our vertical translation. It translates it up or down by k units. H is the horizontal translation. It translates it left or right by h units. So let's see if we can do this here. We can take a look at some graphs that have been translated and see if we can figure out, what's h, what's k, how have we shuffled this thing around, okay? So describe the translation that have been applied to the graphs of f of x to obtain the graph of g of x. So that's letting us know f of x, we're treating it like the original, g of x is the image. So we transformed f of x into g of x for both of these, not the other way around. State the values of h and k and write the equation of g of x in the form y equals f of x minus h plus k, right? So notice it's just saying, this is not saying we actually have to write the proper full equation for this parabola, though we will do that. It's just saying, what would you have to do to f of x, right? Being general here, this is function notation. So a vertical, well, I guess first we got to take a look at it. We can pick any point, right? Because all these points should have been changed in the same way, and we know we're just dealing with translations here, no stretches yet. So if f of x equals x squared, right, let's just pick a common point, a corresponding image point here. How about the vertex? That's a nice easy one to see. So it looks like the vertex has been translated horizontally from 0 to -4, so that's 4 units left. And then from there, 1, 2, 3, 4, 5 units down to y equals -5, 5 units down, okay? So a vertical translation of 5 units down. A horizontal translation of 4 units left. Okay, so what does that mean k is? The value of k. If I moved it 5 units down, well, k then must be -5. A vertical translation 5 units downwards means a negative k value of 5. Okay, what about h? 4 units left. 4 units left. So what's our h? Well, how do we move it 4 to the left? We need h to be -4 to slide it 4 to the left. Okay, -4. So what can we write g of x as? Well, in general, for transforming functions, with just translations, again, we're going to add more stuff to this, but in general, for just translations, we say, all right, take f of x, right, and to translate it h units left or right, you're going to subtract your h, okay? And then, to translate it k units up or down, you're going to add your k. So literally all we have to do here is say that g of x is a lot like f of x, except instead of just being f of x, obviously, it's f of x minus -4. So minus -4, right? That's going to give me plus 4. Plus 4. Okay? And then add k to that. Well, k is -5. So if I add -5, that's going to subtract 5 here, right? And notice how powerful this is, because what this is doing, again, this is not the full proper equation. You couldn't graph this, right? It's not the full proper equation. We know this is a parabola. It's going to have some equation like y equals, x plus 4 squared minus 5, right? But what it's saying is it's a description in terms of the original function f of x. It still kind of relies on saying it's like f of x, okay, but translated 4 units left and 5 units down, okay? That's why this f is still here. It's saying g of x is like f of x if instead of x you had x plus 4, and then you subtracted 5 from that. Right? And notice again, this is really handy because once we know how to read this, we can say, all right, so it's just been translated. H is -4, so 4 units left. K is -5, so 5 units down. There we go. All right, so let's try this one out. This is kind of a funky looking graph of a function. This would obviously, this one wouldn't even really have a nice continuous equation. We'd never be able to find the equation for this one or anything because it's what we would call piecewise, right? We'd have to have a different function here, 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 here. But we can still think about how would you transform this f of x into g of x. Again, we can kind of tell same shape, right? Same shape, it's just been shifted down and to the right. Let's figure out exactly how far. So A has become this A prime, that's its image point. So it doesn't matter which order we look at them. Let's just do vertical first. So it's gone from +2 to -7, right? That is a vertical translation of 9 units downward, right? Vertical translation, 9 units down. Okay, but then from there, it was translated horizontally 1, 2, 3, 4 units. So 4 right. So there we go, horizontal translation of 4 units right. Vertical translation of 9 units down. Can you figure out K and H? Well, K has to do with the vertical, right? So 9 down, that means our K is -9. And 4 right, that means our H is +4, right? To move it to the right, that's X getting more positive, so we must have had a positive H there, 4 to the right. So g of x can be written as, again, use this is like a template, right? It's a template for saying how would you transform the original graph's equation to get this new graph, right? Well, we know that h is 4, so I need to rewrite g of x. G of x in terms of f of x would be f of x minus our h, and our h is 4, x minus 4, plus k. But k is -9, right? Plus k, but k is -9, so subtract 9. And that's the equation of g of x in terms of f of x. Again, this is not the equation for g of x. It's not like you could put this into your calculator and graph it or something like that, but it is a description of how to get to g of x from f of x. We will write equations, not so much, a little bit today, but mostly tomorrow, equations of transformed functions, like we would actually write the equation for this new parabola, okay? But that's not what we're trying to do here. We're just saying, you know, in terms of f of x, this is how you would need to transform it to get this transformed equation g of x, right? In this one, we didn't necessarily know the equation of f of x, though we did. It was x squared, right? But we're not trying to write the equation of this new one. We're just trying to say, what would you do to f of x, right? Well, you would replace x with x plus 4, and then you'd subtract 5 from the result. So same thing here. So that is the equation written for g of x in that function notation for transformations. That's g of x in terms of f of x. Notice, again, same thing. We can pick out h. H is +4, so 4 units right. We can pick out k. K is -9, so 9 units down, right? Very handy instructions on what to do to the graph and or the equation in order to transform it in these ways. Alrighty, let's try another one here. The graph of the function f of x equals x squared is transformed into y minus 6 equals f of x plus 1. Now hang on a sec. This is where they sometimes try to trick you, right? You do often see it written this way. Personally, I prefer to just rewrite it so that it really does look like, you know, x minus h plus k, right? And we can pretty quickly do that. It's just that they've got k, they've done y minus k. We can see that if we just add 6 to both sides, we could rewrite this as y equals f of x plus 1, talk about that in a sec, plus 6, right? If I add the 6 to both sides, so plus 6. And there we go. I always recommend with these, just rewrite it in the way that we usually look at it. It's just we get a little more comfortable with that. To me, it makes a little more sense too, because now I can see, oh yeah, we're just adding 6. Like y is equal to this stuff plus 6. So that's going to move every y value up by 6. Okay? So it asked us, what is the new location of the vertex? Well, first things first, where's the original vertex? This is the graph y equals x squared. F of x equals y squared. Or sorry, f of x equals x squared, right? Hey, we know that graph very well, having taken Math 20. We know that its vertex is at 0, 0 originally, right? Because 0 equals 0 squared. And then it just goes up from there, okay? So if we know it started at 0, 0, and we know that it's been translated, right? Looking at this in function notation, we can see what's h? What's h? Careful. It's supposed to be x minus h. So if we ended up with x plus 1, h must be negative 1, right? Because then x minus negative 1 would become x plus 1. Minus a negative is how we would get a plus 1 there. So what is that? What is the associated transformation? We know h tells us about the horizontal translation. Okay, and if it's negative 1, 1 unit, which way? Left. Okay, so we've shifted this graph 1 unit to the left. There's k. We can just see it. That's the nice thing about function notation. You can just pick these things out. K is 6. So positive 6. K tells us about the vertical translation. It's positive 6, so 6 units up. All right. Well, that lets us think about this pretty easily then, because if my vertex started at 0, 0, I moved it 1 unit left. What's that new x coordinate? Well, 0, 1 left. It's now going to be at negative 1, right? And 6 units up, starting from 0, add 6, right? It's going to be now at a y coordinate of 6. So we've taken 0, 0, we've gone 1 left to negative 1, and then we've gone 6 up to positive 6. So where's our new vertex? It's going to be at negative 1, positive 6. And there we go. That's the location of the new vertex without having to graph anything there. All right, so here's one, like I said, where we can actually transform the equation itself too. Once we understand how to read this, right, what is it really telling us? It's actually just instructions on what we need to do to this equation to get the equation of the transformed graph. So not just the equation in terms of the original, but actually just the equation for that new graph. So let's try it out. The graph of f of x equals 1 over x cubed is translated 3 units right. So what does that tell me? 3 units to the right, h is positive 3. 7 units down, what does that tell me? K is negative 7. Write the equation of the transformed function. So I always, when I'm dealing with these, first I write it out, right? We're not dealing with stretches yet. This is a bit of a simpler version, but we know that it's going to be y equals, right? To transform it, there should be an f there. Y equals f of x minus h. Well, our h is positive 3. Plus k. Well, our k is negative 7. So plus negative 7 just gives me a minus 7. Okay? When these get more complicated, what I like to actually do is first just figure out what's f of x minus 3. Okay? Now again, f of x minus 3, right? If I said f of x means our inputs are x. If I say f of 2, it means input a 2 wherever you saw an x, right? If I say f of, we looked in the first lesson, or the second lesson of f of g of x. What did that mean? We put g of x wherever we saw an x. So it's actually a very similar idea here. In fact, it's the exact same idea. It's saying to get the equation of the transformed graph, it looks a lot like y equals f of x, except instead of being f of x, it's f of x minus 3. So wherever we see an x in the original equation, if we replace it with an x minus 3, we will have translated the graph 3 units to the right. And then if we take that, f of x minus 3, and subtract 7, we will have translated it 7 units down. So to show you what I mean, right? If I replace x in the original function with x minus 3, right? That tells me I want f of x minus 3. So replace x with x minus 3. And then whatever that is, whatever that gives me, subtract 7 from it. So let's just do that one step at a time. We know that f of x equals 1 over x cubed, right? So what's f of x minus 3? Well, wherever I see an x, I'm going to put in x minus 3. So 1 over x minus 3 cubed. Okay, but we didn't just want f of x minus 3. We wanted f of x minus 3 minus 7. okay? Well, we already know that f of x minus 3 is 1 over x minus 3 cubed. So 1 over x minus 3 cubed minus 7. And that's it, folks. That is the equation. If we were to graph that, and I will graph it in a second, if we graph that, y equals 1 over x minus 3 cubed minus 7, that's the equation of the transformed function. So notice the difference here. Sometimes students aren't quite sure what the difference is between just writing this in function notation, like we did here, and actually getting the equation of the transformed function. This is an equation you could graph, right? We just want to graph everywhere where the y is equal to the 1 over the x value minus 3 cubed, subtract 7, right? You could graph this. You could put it into your graphing calculator and get a graph, or you could graph it by hand as well, right? This one, not quite. This is just saying, here is the transformation in terms of f of x, which is this function here, right? It's just saying, take this thing, f of x, and replace x with x minus 3, and then subtract 7. But we're still depending on f of x, right? This, no longer. This is actually just the equation for the transformed function. If you graph this, it will look a lot like this function, except shifted 3 units right and 7 units down. Let's take a look at that. Okay, so to show you what I mean here, right, I've gone ahead and graphed them both in Desmos. Again, should use your calculator to get comfortable with it for graphing, but just to quickly show with all the colors and stuff here, right? Notice in blue, I've got our original graph, y equals 1 over x cubed. That was f of x. Now, all I've done there is graph what we just did, right? Replace x with x minus 3 and then subtract 7 from the result. Y equals f of x minus h plus k, right? And look what it's done. In red there, that is now the graph of y equals 1 over x minus 3 cubed minus 7. And look, if we pick some corresponding points, right? If we pick a point that we can see nicely, for example, maybe here at 1, 1, right? At 1, 1. Has it been shifted 3 to the right and 7 down? Well, count 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7 down. Sure enough, looks like that's where it ended up. Okay, so it worked, right? That's now the equation for y, for the transformed function, having been shifted 3 to the right and 7 down. Okay, there it is, right there, the image point. It's kind of hard to get it to stay there. Okay, so again, looking at the differences here, okay, this is in terms of f of x. It's general. It's a description of what to do to f of x. Here's what happens when we actually do those things to the equation in order to get our equation for our transformed function. Graphing this just gives us the transformed function. This tells us what to do to the original in order to get the transformed one. This just is the transformed function's equation. Okay, so here's an interesting one where it tells us, it doesn't tell us what the function is, but it does tell us that its domain, the domain of f of x is all values of x such that negative 3 is less than x, which is less than 5. So x needs to be between negative 3 and 5 for this function. And the range is all values of y such that y is greater than 2. So y needs to be greater than 2 for this function. And f of x is going to be transformed into the graph y equals f of x minus 4 plus 7. So again, it's not actually telling us the equation, but it's telling us it in terms of f of x. And if we know how to read this, right, it is in that function notation for transformations, right? Can you pick out h and k? Looks like h is 4, right? And k is positive 7. Because again, just comparing to f of x minus h plus k, 4 is in h's spot, 7 is in k's spot. Okay, so this question asks us which part of the transformation will affect the domain, which part will affect the range. Well, if we think about that, what does domain refer to? Domain refers to the valid x inputs, the x inputs. So what's going to change that? Sliding it left and right with h, or sliding it up and down with k? What affects the x values? Well, the horizontal, right? X is the horizontal axis. So domain refers to x values, so horizontal translations will affect it. Right? In this case, our h, right? The h. Range refers to y values. What's going to change the y values that the graph passes through? Well, only sliding it up or down, right? If y used to be greater than 2, sliding it up 1 would mean y needed to be greater than 3, right? We shifted the whole thing up by 1. Or sliding it up 2 would mean that y needed to be greater than 4, sliding it up by 2. So vertical is going to mess with the y stuff, the range. So vertical translations affect it. Okay, that's going to come from k. So now it asks what will actually be the domain and range of the transformed graph. Well, I mean, we can think about this. We can visualize it a bit here, right? Our domain used to be between -3 and 5. So a horizontal translation is just going to shift every single point by h, right? And here, h is +4. So if we think about it, this used to be our domain, right? From -3 to 5. But what if we shifted every single x value on our graph to the right by 4, right? So h is 4. That gives us a horizontal translation 4 units right. Literally, that means we're adding 4 to every single x value. So -3, right? 1 right, 2 right, 3 right, 4 right. Where is it now? Now it's at -1. This isn't scaled very well, but just giving the visual, right? Nope, sorry, that should be +1. Can't count. +1. Okay. And 5, where is 5 going to end up? Where's going to be the high side of this domain? Well, from 5, 1, 2, 3, 4. 5 plus 4, it's going to end up at 9. Okay. So we've shifted it. It used to be between -3 and 5, but by shifting everything to the right by 4, right, we've shifted the leftmost part of the domain to +1 and the rightmost part of the domain to +9. So our new domain will be the set of all x's such that 1 is less than, always be careful to check, not less than or equal to, strictly less than x, which is less than 9. X is an element of the real numbers, right? There's our new domain. What's our new range? Same idea, except we got to think about how k, that vertical translation, is going to affect the y values. So k is 7, which gives us a vertical translation, 7 units, and it's +7, so 7 units upward. So, again, just drew this out to visualize it, but it used to be, maybe our graph used to look something like this. It went as low as 2, but it never got to 2 or lower, right? But now we've taken the whole graph, every single y value has been shifted up 7. So 1, 2, 3, 4, 5, 6, 7, right? Where is it now? Well, 2 plus 7, it's now at 9. A y value of 9 is where our new kind of minimum for this graph will be. So our range is going to shift 7 units upwards. So it's going to be the set of all y's such that y is greater than 9, right? Instead of 2, 9. And y is an element of the real numbers. And there we go. That will be the range of the transformed graph. Okay, so go ahead and give this one a shot. It's just getting comfortable with the function notation and how we represent transformations. Be careful, right? We want to often, it helps to write it in the form we're most used to seeing it in, which is like this. Sometimes they don't give it to you in that form, but you can always quickly turn it into that form. Hint, hint, taking a look at this one here. Notice they've got the k over here, but we could move it over there to figure out what k actually is. Anyway, try that one out, and there's some more in the formative you could take some time to do now to gain some comfort with this. All right, so let's talk about mapping notation. This is a handy one, especially when we're trying to draw a graph, okay? It's the same ideas, but we represent it in another way. So another way to represent the transformation of a function, because that's all this is doing, it's showing how you go from your old function to the new function, is to think about transforming each point one at a time, essentially, okay? Okay, what mapping notation does is it takes each xy coordinate on the original function and assigns a new coordinate based on the transformation. So it is very much just like instructions. It says here's how you're going to go from an original point xy to an image point that's going to have a new x value and a new y value. Okay, instead of showing us how to alter the equation overall, like function notation does, it tells us specifically how to alter each point, right? So for example, during the translation from y equals f of x to y equals f of x minus 3 plus 4, we can see that h is 3, k is 4. So h is positive 3, meaning each x value is moved to the right by 3. And k is positive 4, meaning each y value is moved up by 4. Okay, now this is going to lose that thing of, feeling opposite about x's here, because again, the mapping notation is a little more direct. It's just saying, what are you going to do to every x? What are you going to do to every y? Okay, well, what we're going to do to every x if we move it 3 to the right is add 3 to it, right? If it used to be at 0, now it's at 3. If it used to be at 7, now it's at 10. We're just adding 3 to it to move it 3 to the right. So this is a little more like literal and direct. It says every x is getting 3 added to it if we translate something 3 to the right. Every y is getting 4 added to it if they're shifting it up by 4. And that's how we represent mapping notation. Notice how it acts like literal instructions on how to go from an original point to the image point, right? Take whatever x was before and add 3. Take whatever y was and add 4. If you had a point at 0, 0, that point is now at 3, 4. Okay, let's try it out. All right, so write the mapping notation for, here it's given to us in function notation, y equals f of x minus 7 f of x plus 1 minus 3. Okay, so first things first, let's figure out what is the transformation being represented here. Okay, well, we can see that, again, if we compare to y equals f of x minus h plus k, right? What's in h's spot? Ooh, a negative 1, right? A negative 1 must be in h's spot so that we ended up with, x minus negative 1 or x plus 1. Okay, so our h is negative 1. H equals negative 1. This is a horizontal translation, 1 unit left. Okay, what is our k? Our k is negative 3. So a vertical translation, 3 units down. So here's what mapping notation does. It says, so how do you go from the original point xy to the new point? How are those xy's going to change? Well, this literally means, right, if h is negative 1, we're shifting everything 1 unit to the left. We're just subtracting 1 from every x. So in mapping notation, we could represent this as xy is going to become, how will the x coordinates have changed? They're no longer just going to be the same x that they were. They're going to be whatever that was, minus 1, right? We've shifted it 1 to the left. And what about the y coordinate? Well, whatever y used to be, we're going to, what are we doing here? To translate it 3 units down, we're literally subtracting 3 from each y value on the graph, right? Just looking ahead here, to move this 3 down, I would have to subtract 3 from the y value to move it from a y of 4 to a y of 1. Okay, so instead of being the y where it used to be, it's going to be that y, but minus 3. And that's mapping notation, right? It's instructions on how to transform each individual point. Take a point xy and turn it into that x minus 1 and that y minus 3. Let's try another one here. Ooh, they're trying to trick us, right? Notice, okay, y equals f of x minus h plus k. This is typically, I find anyway, the easiest way to think about it. So let's just rewrite it that way. Let's subtract 4 from both sides so that it's written in the form we're a little more used to. And that'll give us y equals f of x minus 2 minus 4. And now it's a little easier to compare and not mix up the sign on our k and that stuff. So x minus h, we've got x minus 2. So h is 2. giving us a horizontal translation 2 to the right. What's k, and what does that mean? K is -4. So a vertical translation 4 units down. In mapping notation, what does that mean? To move x's 2 to the right, what do you have to do to them? Right? I'm just going to borrow this grid here. If I want to move this point here 2 to the right, what do I have to do to that x value? I've got to add 2 to it, right? If it was at 1, now it would be at 3. Okay, so start with a point, any point on your original graph, x, y, and to find the corresponding image point, you're going to add 2 to the x value, and you're going to subtract 4 from the y value in order to move it down by 4 units. And that's mapping notation for that one, right? Literal instructions on how to go from your original point to the image point. Take the x's, add 2, take the y's, subtract 4. All right, so here's another one, a little bit like what you might see on the diploma or a unit test in terms of numerical responses. Okay, let's try it out. The graph of y equals f of x is shown below as the solid line. So this is the original f of x. The transformed graph, g of x, is shown as the dashed line. Okay, so when written in mapping notation, this transformation is written as xy to x minus a, y minus b. The values of a and b are blank and blank. Okay, so all that's saying is we've got to figure out what number goes here and what number goes here, and then we're going to record those two numbers as our answer. We'll talk about recording it when we actually get the answer. But in order to do that, let's figure out, we can see this is just translations, right? It's just been shifted, looks like x minus a, so that's kind of a hint. It's been shifted to the left. In mapping notation, if this became x minus a, we're subtracting whatever a is from every x value. And then similarly, it's been shifted down by whatever b is, right? Because it's y minus b. So that's a nice little hint they've given us. Can we figure out what a and b are? Well, let's look at the graph. Pick a point, any nice easy point that's easy to track. Could use this one ending up there or this one ending up here. Let's just use the top. Why not? I'll use the top. So it's been shifted 1, 2, 3, 4 units left, 4 left, right? So our h, what we would normally call h, is -4. And then it's been shifted 1, 2 units down, 2 units down. So k is -2. All right. Well, that means, right, again, what are we doing to each value of x and y? Starting with the original points, x, y, we can map them to the new x's will be what we started with, but we're shifting them all 4 to the left, meaning we're subtracting 4 from every x value. Whoops, too early for that bracket. Okay, what have we done to the y values? We've shifted them all down 2, so we've subtracted 2 from every y value. So the new y values will be the original ones, but then subtract 2 from them. And there we go. That's in mapping notation. So they asked us for our answer in the form, right? They said, you know, your answer is going to look like this is essentially what they're saying. And then they're asking us, when you write it like this, what's A, what's B? Well, what's A? It's 4, right? X minus 4. So A must just be 4. What's B? Y minus B is Y minus 2, apparently. So what's B? It's 2. So the values of A and B are 4 and 2. And how do we actually record that as a numerical response? So this is something students sometimes do. They're not sure. They don't need all 4 boxes. You're always given 4 boxes, okay? We don't need them all. We only need 2, right? We need to put a 4 and a 2. So always start in the first box. If you don't need these ones, that's fine, okay? Sometimes students do this. They say 4, 2, right? No, always start in the first box. So we would just, on a numerical response, this were the diploma or a unit test in SmarterMarks, whatever it might be, we would start in the first box, 4, 2. We don't need those last 2, and that's fine. Okay, so there we go. Go ahead and give this one a shot. It describes a transformation. Sorry, it gives you the function notation, and then it asks you to say what transformations are being applied. And then it also asks for it in mapping notation. And then you can try out some other ones that are similar if you're wanting more practice now, or again, you could save them till later after the lesson. Okay, so now let's keep moving on this path of looking at transforming graphs. We've kind of talked about translating them, sliding them, okay? We're going to talk now about stretching them. Something, again, that you did in Math 20. We'll actually start out with a Math 20 kind of example here. So far we've looked at translations of graphs, where the graph essentially slides horizontally or vertically. What did that involve? Notice we were always just adding or subtracting a constant to each x and or y value, right? I mean, really we were just adding them, and sometimes they were negative, so we were adding a negative, okay? And that shifted our x or our y values left or right, because we were just adding stuff to it. But they were still all equally spaced, right? Everything got the same thing added to it or the same thing subtracted from it. What we're now going to look at is stretches, specifically vertical stretches. We're going to do horizontal stretches, but that will be in the next lesson. Okay, we're going to do vertical stretches because those you've seen before in Math 20. So now let's look at what happens when we stretch a graph. Now, to stretch a graph, like the name suggests, we're actually going to change its shape, right? If you take a ball of Play-Doh and you stretch it, you've changed its shape, okay? In order to stretch a graph, we don't add or subtract something to each x or y value. We actually multiply every x or y value by some constant, okay? Like I said, we'll start with vertical. We're going to save horizontal for the next lesson, okay? But when the output of a function, when our y values, probably shouldn't be too shocked that it is a y value for a vertical stretch that gets multiplied by something, right? In order to vertically stretch something, we want to change its y value, multiply y by something. And so for a vertical stretch, we multiply it by a non-zero constant. A is what we give that name. So these are called parameters. They're just, placeholder symbols that we use to represent different things we could do to a graph. So we saw H for horizontal translations, K for vertical translations. Here now is A for vertical stretches. A is actually the same as what you used in Math 20 for the vertical stretch. So the result, if I take y equals f of x and I transform it into y equals a times f of x, it's a vertical stretch of the graph about the x-axis by a factor of the absolute value of a. We're going to see later on what happens when a is negative, but even when a is negative, there's still a vertical stretch by a factor of whatever a's value is. Do you remember absolute value from Math 20? Remember, all that means like the absolute value of -1 is 1, the absolute value of 1 is 1, the absolute value of, -12 is 12. It basically just, if it's negative, it makes it positive. If it's positive, it leaves it alone. So all we're saying is the size of A can tell us how much it's being stretched by, okay? If A is negative, like I said, it will also cause a reflection across the x-axis. We'll talk more about that later. For now, we're going to focus just on the stretching side of things, okay? In other words, every y value on the original graph is just multiplied by A. It's a vertical stretch, right? Vertical translations added something to every y value. Vertical stretches multiply something by every y value. Every single y value on the original graph is multiplied by A. That's really all that is happening in a vertical stretch. Okay, so let's get our, dip our toes back into this by revisiting something we talked about in Math 20, from some familiar territory before we take it into new places. You explored this in Math 20-1 with parabolas as well. Recall that vertex form for a parabola is y equals a times x minus p squared plus q, right? Where a represented our vertical stretch. It meant that in Math 20, it means the same thing now. The number that each y value is multiplied by. So there's some examples below here. Just to keep things simple, I just labeled 1 point as we stretch the graph, as we change the value of a, okay? So, and that is the point that is originally at 2, 4. But as we go, you can check for yourself. Every single y value is just being multiplied by whatever the a is in each example, okay? So, this makes a ton of sense when we think about it, okay? If my base graph here is y equals x squared. So a is 1, right? Compared to y equals x squared, every y value has been multiplied by 1. Unsurprisingly, that means it just still looks like y equals x squared, because multiplying by 1 is not going to change those y values, right? So it looks like this. It passes through the point 2, 4, because 4 is equal to 2 squared, right? So that point should be on the graph of y equals x squared. Now look what happens if we change y equals x squared if we make a equal 2, right? If I'm transforming this from y equals f of x into y equals a f of x, notice what we're doing there. We're literally just multiplying the equation by a. Well, if y used to be equal to x squared, now it's no longer equal to x squared. It's equal to x squared times 2, right? So what happened to every y value when we compare it back to this one? It just got 2 times bigger, right? It used to just be x squared. Now it's 2 times x squared. Every single y value compared to this one just got multiplied by 2. So notice what happened. The point that was at 2, 4 is now at 2, 8. Our graph is going up more quickly. It's been stretched vertically, okay? That causes it to end up like horizontally. It ends up looking narrow. Like if you imagine stretching some Play-Doh vertically, it gets skinnier in the middle, right? Because it's going up faster, right? So what was at 2, 4, the new y value is 8. When x is 2, now y is 8. Checks out with the equation as well, right? X used to be, if I used to be, I just squared 2 and got that y was 4. Now I'm squaring 2 to get that y is 4, but then multiplying it by 2 to get that y is actually 8, right? So notice, all we've done here, we've multiplied y by 2. Okay, what if we made a 3? So instead of writing y equals x squared, my equation becomes y equals 3x squared. Well, you can probably predict, right? Compared to this graph, where y was just equal to the x value squared, now y is equal to the x value squared, but then times 3. So every y value just got 3 times larger on this graph compared to what it was on this graph, right? Sure enough, that point that was when x used to be 2, y would be 4. Now on y equals 3x squared, when x is 2, y is already all the way up at 12, right? 3 times bigger than 4. Because, again, 2 squared is 4, times 3 is 12. So every single y value here has been multiplied by 3. Again, I only labeled 1 point to keep things simple, but check for yourself. Look, when x was 1, y used to be 1. Now when x is 1, y is 3. It's 3 times higher. Every y has been multiplied by 3, right? Over here, when, x was negative 2, y was 4. Now, when x is negative 2, y is 12, right? 3 times higher. What if we made a something smaller than 1? Or I should say, between 0 and 1, right? I make it 1/2, okay? What's that going to do? Every y value gets multiplied by a. So wherever y used to be on the original graph, y equals x squared in this case, right? That y coordinate for every single point has now been multiplied by 1/2. So it used to be at 2, 4. Where's it going to end up? 2, 2. Because 4 times 1/2 is just 2, right? And again, sure enough, used to be that y was just equal to x squared. Now it's equal to half of whatever x squared is. So it makes sense that every y value is now half as large by making that vertical stretch, that a value, be 1/2. Okay? And that's all a vertical stretch does. It multiplies every y value by a. So how do we represent this? Okay, the function notation for vertical stretches is written as y equals a times f of x, right? Literally what this is saying is take your original function, its original outputs, and multiply them all by a. That's telling us, take every y value, multiply it by a, okay? We're eventually building up to, here's where we're building up to, a little preview of the future. We're eventually going to have many of these going on. So we now see y equals a times f of x, but we're eventually, earlier we saw this, we're going to deal with them as well, okay? X minus h and plus a k. In fact, it doesn't stop there. Tomorrow, or in the next lesson, we'll also talk about a horizontal stretch, a b, and that's going to go there, okay? So we're building this up piece by piece. For now, we're just focused on the vertical stretch, the a part, okay? So y equals af of x, that's function notation for a vertical stretch. Mapping notation, remember, mapping notation is a little more direct. It's really like instructions. If you had a point x, y, to get the new transformed image point, what do you do to each thing? Well, x gets left alone, right? We're vertically stretching it. We're multiplying the y values by a. We're not doing anything to the x's, right? So x is still whatever x was before, but y has become a times y, right? Y has become a times y. That checks out, right? When a was 2, y used to be 4, now it's 2 times 4, or 8. Okay, so in both of these, a just represents our vertical stretch, right? For example, if a graph y equals f of x is vertically stretched by a factor of 4, that's how we say that, vertically stretched by a factor of 4. Each y value is multiplied by 4. And this transformation could be written as y equals 4 times f of x, that would be function notation, or in mapping notation, xy has become x 4y. Every y has been multiplied by 4. Small note on stretches, but a helpful one I find, okay? And there are definitely some videos posted in the agendas and stuff that don't follow this. No matter what, we're going to call it a stretch. I know it's tempting to say that it's been compressed by a factor of 1/2, right? But what gets confusing with that then is, what does it mean to be compressed by a factor of 1/2? Does it mean, it's 1/2 as stretched, or does it mean it's 1/2 as compressed? Like, does that mean it's actually less compressed, meaning that it's more stretched, right? And so see how that terminology can get confusing, right? So we wouldn't say it's been compressed. We always just say it's a stretch, and we let the number tell us whether that means it got, stretched to be taller vertically, or stretched in such a way that it actually got, shorter, so to speak, and looks like this. So always say stretch and let the number tell you what that means, right? Vertically stretched by a factor of 1/2, we know that just means every y value got multiplied by 1/2. Vertical stretched by a factor of 2, we know every y value got multiplied by 2. Okay, let's try some out. And some important terminology I just wanted to come back to quickly here for vertical stretches, okay? We say it's been vertically stretched about the x-axis. Sometimes that throws students off. Why is it about the x-axis if it's a vertical stretch and we're changing the y values? What about the x-axis means is that's where we're kind of stretching from, so to speak, right? So like if I had a parabola that I was going to vertically stretch, now, we don't do it in Math 30, but technically it is possible to vertically stretch it about the line y equals 2, let's say, right? And what that would mean is that from y equals 2, I'm going to stretch these upwards maybe, stretch those upwards, and I'm going to stretch this part downwards, right? From the line y equals 2. Now, we don't do that. We always stretch about the x-axis in Math 30, right? You can kind of envision taking these and pulling them up. They're fixed here, and you pull them up this way, and fixed here, and you pull them down from there. So we don't do that, but that's why it's always specified still that it's about the x-axis. So don't get thrown off about the x-axis. It is a vertical stretch. It's just that what we're saying is we're kind of stretching it from the x-axis, right? Imagine it's like it's held in place here, right, where those invariant points would be, and then we pull these parts, we vertically stretch these parts away from the x-axis, and this part gets stretched away from the x-axis, or towards, I suppose, if a is less than 1, okay? But that's what it means by about the x-axis, almost like away from the x-axis, or in the case of, an a being smaller than 1, kind of towards the x-axis. So don't let that throw you off. Yes, it's a vertical stretch, right? A stretch about the x-axis is just kind of telling you where almost like your anchor point is that you're stretching from. So here we've got a graph and a table of values for y equals f of x. So that's our original function. Complete the table of values for y equals 2f of x. So what does that mean? That means our a is 2. We vertically stretched this by a factor of 2, right? So what does that actually mean for what's happened to every y value? each y has been multiplied by 2, right? We did it with translations. We said every x had this added to it, every y had this added to it. Now for stretches, it's just every y value has been multiplied by this a. Okay, so you can see here, right? To go from y equals f of x to y equals 2f of x, we have to take our original y's, our original f of x outputs, and multiply them all by 2. We're not doing anything to the x's, right? There's no horizontal stretch. That's going to come later. Vertically stretched, y values are being multiplied by 2. So we were given a table of values. That was nice of them, right? I mean, we could have actually just even used the graph, but let's take advantage of this. So the point that was originally at negative 6, 4 is going to be at negative 6. Well, multiply the y values by 2. So 4 times 2 gives us a new y value of 8. So there's a point on our graph. This one that used to be at negative 6, 4 will now be at negative 6, 8. Negative 6, 8. Maybe I'll do it in red so it stands out a bit more. There's 8. Okay, and we could just keep continuing on like that. 0 times 2 is still going to be 0. Hey, do you have any idea what we might call a point like that didn't change? We did a transformation and its location didn't change. It was at negative 2, 0. It's still at negative 2, 0. That's right. We could call this an invariant point. We'll talk about those a little bit as we go. Invariant. So for a vertical stretch, since we're multiplying every y by some constant, well, wherever y is 0, the only number that you can multiply by something and not change what that number was is 0. 0 times anything is still 0. So wherever we have x-intercepts where y is 0, those are going to be invariant to a vertical stretch, okay? But moving on with graphing this, that point stays put at negative 2, 0, okay? 0, 2 is now going to be found at 0, 4, because 2 times 2 is 4, right? So 0, 4 is a point on the stretched graph. Okay, another invariant point, 2, 0. We can even, just to mix things up a bit, let's just look at the graph. This one has a y value of 0, right? So multiplying that y value by 2, it's still at 0. 0 times 2 is still 0. Okay, looking at this one here, it's at 6, 4. So multiplying that y value of 4 by 2, it's going to be at 6, 8. So we just looked at the graph for those. Oops, 0 and 8. Okay, we could even fill in, we could use the graph to fill in some of the blanks. I mean, we can kind of tell this is just sort of a W shape, but notice any point on the graph, its y value is going to get multiplied by 2. So for example, this one here was at 4, 2. Now it's going to be at 4, 2 times 2, or 4, 4. Every y value is getting multiplied by 2, right? This one here, y value of 1. Well, 1 times 2 is 2. So now its y value will be 2, right? And if we, again, I should really use a ruler here, but the ruler does not work very well on my iPad screen. So I'll do my best to just draw some straight lines. Okay, and there we go, sort of. Okay, that is that graph having been vertically stretched by a factor of 2. And you can tell that looks right, I think, right? It looks like it has been pulled upwards, vertically stretched upwards by a factor of 2, right? It's gotten taller, so to speak, okay? All we did was multiply every y value by 2, because that's what a vertical stretch does. Okay, so this one kind of just builds off of that question. For the previous question, state the domain and the range of both the original and the transformed function. So the original was called f of x. So for f of x, what's our domain? Well, they gave us the graph, okay? And we can see that it stops at negative 6 on the x-axis and positive 6 on the x-axis, right? It's only defined, it looks like, for values of x between negative 6 and positive 6. It's undefined beyond that. There's no graph of it, meaning it's undefined beyond there. We don't know what it does beyond those. Seems like it just doesn't exist. So the set of all x's such that negative 6 is less than or equal to x, which is less than or equal to positive 6. Again, less than or equal to because it actually gets to 6. It's got a closed dot there, meaning it does get to 6. It just doesn't go beyond 6. Okay, so x is an element of the real numbers. For its range, same thing, but for y values now. So the set of all y's such that, well, the lowest it ever gets on the y-axis is 0, right? It never goes down into the negative y's. So the set of all y's such that 0 is less than or equal to y, which is less than or equal to, and the highest it ever gets on the y-axis is positive 4. And y is an element of the reals. Okay, what about for the transformed function, for 2f of x? Well, take a look here. Has the domain changed? No, right? That's not very surprising because a vertical stretch, we're not multiplying the x values of each point by anything, right? We're leaving the x's alone. We're multiplying every y by 2 for a vertical stretch. So it's still going to go from negative 6 up to positive 6. We can see that from the graph as well that we just made. The set of all x's such that negative 6 is less than or equal to x, which is less than or equal to positive 6. X is an element of the real numbers. Could use interval notation here as well if you like. Okay, and the range, whoops, I didn't write domain there. Don't have room now, sorry. The range, the set of all y's such that, oh, now this has changed. Still from 0, still 0 is the minimum, right? But now it goes up twice as high. Instead of only going up to 4 on the y-axis, it's going up to 8. See that on our graph, right? Now this actually makes a ton of sense. What did we do? We multiplied every y value by 2. So if our old minimum was at 0, we'll multiply that by 2, still at 0, right? But our old maximum used to be at 4, multiply that by 2, now it goes up to 8, right? Visualize stretching this graph by a factor of 2, every y value getting multiplied by 2. That's going to essentially, multiply the ends of our range by 2 as well. They're part of the graph. Those are the y values, but now this is twice as high. You can think of this as being twice as high as well. It's just that twice of 0 is still 0. All right, so hopefully that makes sense, right? That the range would have changed in that way, but the domain stayed the same because we didn't do anything to mess with those x values. All right, one more here and then you should try this out. But the graph of f of x equals absolute value of x is vertically stretched by a factor of a to give the graph of g of x, as shown below. So f of x, this is the graph of absolute value of x, right? Looks like the line y equals x, except wherever y would have been negative, it's positive because we're taking the absolute value of x, right? So when x is negative 1, y is positive 1, because the absolute value of negative 1 is 1. When x is negative 4, y is positive 4. Absolute value of negative 4 is positive 4. Okay, so it's vertically stretched. We want to determine the value of a and the equation of g of x. So this is one where we're not only going to figure out what a is, kind of do it in function notation, right? But also actually get the graph of the new, the equation of this new graph, right? Not in terms of f of x, but just its own equation. So let's take a look here. What happened to every y value? Because we know it was vertically stretched, right? That's nice. They told us it's vertically stretched by a factor of a. So we know we're looking for something that every y value got multiplied by. I mean, really, it kind of just takes a couple points here, really 1 point, right? The right point. If we used to have 4, 4, for example, where is that point now? When x is 4, looks like now y is 12. 4, 12, right? So 4, 4 became 4, 12. What happened to the y value? It was multiplied by 3, right? Could try another one just to confirm. How about this one? We used to have, be careful, this is scaled by 2, so negative 4, negative 8, so this must be negative 6. So negative 6, same thing on the y-axis, 4, 6, 8. So this must be positive 6 for the y-coordinate. Where's that point now? It's now all the way up here at negative 6, 18. So we could keep doing this all day, but we'll see that each point has had its y coordinate multiplied by 3, right? Negative 6, 6 has become negative 6, positive 18. 6 times 3 is 18. 4 times 3 is 12, right? No matter where you look on those two graphs, you'll find that on g of x, the y values are just 3 times larger than the y values on f of x. So what does that mean? A equals 3, right? This is a vertical stretch by a factor of 3. Every y has been multiplied by 3. So that was part of the question, was determine the value of a. That was not so bad. But now it wants us to determine the equation of g of x, right? Well, we're told the equation for f of x. We know that f of x equals absolute value x. And again, function notation kind of tells us how to get the transformed equation. Now this one, it's not so bad. We know we're just multiplying every y by a. So if every y used to be equal to absolute value x, it's going to be equal to a times absolute value x. But again, all we're saying here, right, for the transformed equation, so g of x, right, for g of x, y is going to equal a times f of x. That's the general form for doing a vertical stretch, right? Again, we're going to eventually add more stuff in, just looking back at what we talked about. Where did we talk about that? Right, we're going to eventually, I erased it. We're going to eventually add more stuff in here. We looked at minusing h and adding k as well, okay? But those are instructions. It's saying to get the equation of the transformed graph, take the original equation and multiply it by a. So the original equation was absolute value x, and now we know that a is 3. So y equals 3 times the absolute value of x is the equation of g of x. I guess I could write it as g of x equals 3 times the absolute value of x. Okay, and that isn't dependent on f of x, right? We know g of x is 3 times f of x, but this is now an equation I could just graph. Let's take a look at it. All right, so in blue here, I've got the original, right? You can see on the left there, f of x equals absolute value x. And then in red, that's the equation of the transformed function that we came up with. G of x equals 3 times the absolute value of x, right? Now notice that doesn't depend on us knowing what f of x is. I mean, we needed to know what f of x was in order to find that equation, but now that we know that equation, we can just graph g of x, right? So there is f of x in blue, vertically stretched by a factor of 3, gives us g of x, which just has the equation 3 times the absolute value of x. So now go practice this, try this one out. It asks you to figure out what transformation must be applied, and then write the equation in the function notation, right? This form, okay? And you can try out some other ones, or again, save them for the end of the lesson, but good to practice as you go while it's fresh in your brain. Okay, last thing we'll talk about here in this lesson are vertical reflections, or more commonly we say reflections across the x-axis. Okay, so vertical reflections across the x-axis can also be caused by the value of a. So you don't need to learn a new parameter here. It's still actually because of a. They occur when a is negative. In other words, when a is less than 0. So in a vertical reflection, we call it a reflection because it's like a reflection in a mirror, right? Each point on the original graph is mirrored across the x-axis, and the x-axis acts as the mirror. So taking a look, there's a vertical reflection across the x-axis. Do you kind of see how it's like, you know, a mirror image? If the x-axis, if we put a mirror here, right, the image of this would kind of look like this one, okay? But why? Why does this happen when a is negative? It makes a ton of sense when we put together the ideas we've been talking about, okay, with a couple other facts that we already know. But let's consider these points. All y values above the x-axis are positive, right? All y values below the x-axis are negative, right? Here's the positive y's, here's the negative y values, okay? Above the x-axis positive, below negative. each and every single y value, when we vertically stretch something by a factor of a, each and every single y value gets multiplied by a. That's what happens in a vertical stretch, okay, or a vertical reflection. When you multiply a positive number by a negative number, you get a negative answer, right? Positive times negative is negative. If you multiply a negative number by a negative number, you get a positive answer. Negative times negative is positive. So why does this cause a reflection? That's the ideas we need to think about. That's enough to make this make sense, hopefully. Because a positive y value up here, if I multiply it by a negative a, which again, in a vertical stretch, every y value does get multiplied by a. So if a positive y value gets multiplied by a negative a, well, positive times negative is negative. So if we had a positive y value times it by a negative a, it's now a negative y value. It's been flipped across the x-axis. And vice versa. If I had a negative y value like here, and I multiply it by a negative a, well, a negative times a negative is going to give me a positive. So any y value that was negative gets made positive, reflected up across the x-axis. Any y value that was positive gets made negative. It gets reflected down across the x-axis, right? So that's summarized here. When a positive y value above the x-axis is multiplied by a negative a, it becomes negative. Now it's below the x-axis, reflected across it. When a negative y value, one that's below the x-axis, is multiplied by a negative a, negative times negative is positive. So now it's above the x-axis. So in other words, any y value, if I multiply it by a negative a, it's going to change the y value's sign, right? If it was negative, now it's positive. If it was positive, now it's negative. Negative times positive, negative. Negative times negative, positive. Resulting in it swapping from one side of the x-axis to the other, right? So you can see that in action here. We were kind of already looking at this one, but again, right? My x-axis is just here. This is the x-axis. That's where y's go from being positive to negative or negative to positive, depending on which way you move. And notice in this one, if I had y equals f of x versus y equals negative f of x, you can see that a there, our a value is just -1, right? Y equals a f of x is how we represent a vertical stretch, meaning that literally every f of x, every y has just been made negative. We've been, well, I shouldn't say been made negative. It's been multiplied by -1. And its sign has therefore changed. So look at this. The point that used to be at 2, -1 has been flipped up across the x-axis to now be at 2, +1, right? How about this point here that used to be on the original graph at 0, 3? Well, 3 times -1 is -3, so now that point is at 0, -3. Okay, they've just been flipped. Reflected, right? Notice, again, if I draw in the x-axis, these points are equidistant, like we saw with reflections in the line y equals x for taking the inverse, right? They've just been mirrored. The same way your reflection in the mirror looks just as far into the mirror as you are out of the mirror, right? These points have been reflected across. So the notation for vertical reflections, there's nothing new to learn here, actually, okay? Because it's the exact same as for vertical stretches. And that shouldn't be too surprising because both stretches and reflections, vertical ones anyway, are caused by A. So it's the size of A that determines the amount of stretch, and it's the sign of A, sign as in positive versus negative, okay, that can cause a reflection. So how big the value of A is, the absolute value of A is, tells us how much it's been stretched by, and whether it's positive or negative tells us whether there's also been a reflection that's occurred. So for example, right, just looking at one here, if a graph y equals f of x is vertically stretched across the vertically reflected across the x-axis without also being stretched, then each y value is just multiplied by -1. It is possible to stretch and reflect it, right? If a were -2, then every y value gets multiplied by -2. So that is going to change the sign of it. That is going to reflect it across the x-axis, but it's also going to stretch it vertically by a factor of 2. So we will look more and more as we go at combining transformations. For now, we're kind of just focused in on doing one at a time. Right now, it's reflections. Okay, so we could represent this in function notation. Same thing. Notice, folks, this is still y equals a times f of x, exactly what we were doing with vertical stretches. It's just that a is -1. So in function notation, a vertical reflection with no stretch or anything else happening just looks like y equals negative f of x. Take your original function, multiply its outputs by -1. In mapping notation, take your original point xy, make the y value have the opposite sign. Multiply it by -1, right? So if this was a negative number to begin with, now it's positive. A negative negative is positive. If this was a positive number to begin with, now it's negative. A negative positive is negative. All right, let's try some out. Alrighty, so the partial graph of y equals f of x is shown below. Sketch the graph of y equals negative f of x. So let's just establish, what are we doing here? Well, what's our a, right? This looks like y equals f of x, except there's an a value. What is that a? It is -1. So this is a reflection across x-axis. We can call it a vertical reflection if we like as well, okay? But it's a reflection across the x-axis, vertical, flipped across the x-axis, okay? What does that mean in terms of what we're going to do to every y? Each y value multiplied by -1, right? We always just multiply the y value by a if there's an a value. Here, we can see that our a is -1. So, you know, picking out some points, just going to pick nice points that are easy to see and we don't have to estimate. 2, 10, where's that going to end up? 2, -10, because 10 times -1 is -10. Sure enough, right? Notice how that looks like a reflection across our x-axis, right? If that's our x-axis, this point has been reflected over there. Okay, let's just get a couple more points. How about this one? 0, 4, where's that going to end up? 0, -4, right? 0, -4. Okay, how about this one? -3, -5. -3, -5. I need to multiply every y value by a, and a is -1. So -5 times -1 is +5. So now this will be at -3, +5. Right? For a line, we really only need a couple points, and then we just pull out our ruler and connect them with a straight line, right? I mean, I could do one more here. -2 is now going to be at +2, right? And again, like I said, I should really use a ruler, but it doesn't work that well on the iPad. So just going to do my best to connect them with a straight line. Something like that. Oh boy, got a little curvy there at the end. Okay, there is the graph of y equals -f of x. This graph now reflected in the x-axis. And notice it looks like it's been reflected, right? This has been reflected down there. This has been reflected up here. Hey, look what point is the same between our two graphs. Looks like the x-intercepts are still the same. Does that make sense, right? That point would be invariant to a vertical reflection in the x-axis? I think so, because the y value there is 0, and 0 times -1 is still 0. So that point won't have moved, right? We're not doing anything to x. All we're doing is multiplying y by -1. So if it was at 0 before for the y coordinate, it's still at 0. Invariant point. Okay. Last example here for the notes, and then we'll talk about something we've already been talking about, which are invariant points. But let's try this one out. The partial graphs of y equals f of x and y equals g of x are shown. All right, there they are. Describe the transformation that must be applied to the graph of f of x to obtain the graph of g of x. Then write the equation for g of x in the form y equals af of x. So write it in terms of f of x. We don't actually have to write the equation for g of x. We just have to write basically what would we need to do to whatever f of x's equation is to get it. We don't even need to know f of x's equation. We're just going to write it in terms of f of x. Okay, well, what's happened here? Can we kind of do some investigating and see? So y equals f of x, well, one thing I noticed, it used to have a point at, what is that, 3, 5? Looks like And this is key as well, folks. Make sure you find a point that actually matches. Like, don't say, oh, 3, 5 became this point, right? That doesn't match up. But we can kind of see, all right, there's like this vertex here. This one has a vertex here. So it looks like 3, 5 has ended up here. That's a theory we can have, and then we can explore it further. So 3, -5. That seems like the y values have been multiplied by -1, maybe a reflection across the x-axis, okay? Ooh, look at these. These are some clues as well. Look at the points that are the same between the two graphs, that didn't change after whatever transformation happened, or at least that they still share, right? 8, 0, and -2, 0. So that checks out with our theory that maybe this was a vertical reflection across the x-axis, that every y value was just multiplied by -1, because we would then expect g of x to have the same points when y is 0, because 0 times -1, still 0, okay? Maybe, what about here? Let's look what's going on here. So this point on g of x is now at -7, 5. -7 is the x value, 5 is the y value. On f of x, there's a point here that was -7, -5. Okay, so I'm feeling pretty confident now that it looks like this is a vertical reflection across the x-axis, right? What have we done to go from f of x to g of x? Every y value has just been given the opposite sign, right? It's been reflected across the x-axis. This point here at a y of +3 corresponds with this original point here at a y of -3, right? So every y value has just been flipped across the x-axis, a vertical reflection across the x-axis. So it looks like, okay, describe the transformation that must be applied. Well, each point on g of x corresponds to a point on f of x, but with the y coordinate having been multiplied by -1, right? So that means we have a vertical reflection, a vertical reflection across the x-axis, right? Maybe I should reword that to actually address their question. How do we go from f of x to g of x? So to obtain graph of g of x from graph of f of x, vertically reflect across the x-axis. Okay. Now we want to state the range of both the original and the transformed function. So range, all right, let's take a look. How did the range change here? Well, originally on f of x, it looks like there's arrows here indicating that it extends forever down and left and forever down and right. So it looks like it goes as low, it approaches -infinity, okay? So for f of x, the range would be the set of all y's such that, well, it goes as low as -infinity, but it does never go above 5. So that means our y values are always less than or equal to 5, right? Anything less than or equal to 5 is part of this function's range. Okay? Or again, in interval notation, we could say from -infinity up to 5. Square bracket on the 5 because it can actually be 5. All right, g of x, let's take a look at it. The set of all y's such that, oh, very interesting. Look at this. This one extends upwards forever, up to +infinity, but it never goes lower than negative 5. This one never went higher than positive 5. This one's never going to go lower than negative 5. So this one has a range of y must be greater than or equal to negative 5, and y is an element of the real numbers, right? Again, or in interval notation, we could say from negative 5 up to positive infinity. Now, doesn't that actually make a ton of sense, right? We've essentially swapped two things here. It used to have a max, now it's got a min. Well, we flipped it upside down. So that kind of makes sense. And that max used to be at positive 5. Now our min is at negative 5. Well, again, that makes sense. We've multiplied every y value by negative 1. So it's now come down to, right? Was at positive 5, now it's at negative 5. It never gets lower than negative 5, as opposed to never getting higher than positive 5 before the transformation. Alrighty, and to finish up here, let's just talk about something that, again, has come up quite a bit already, but we'll formally address it now. Invariant points for when we vertically stretch or reflect. Remember, what's an invariant point? Generally speaking, they don't vary, right? They're points on a graph that remain unchanged after a transformation is applied to it. Okay? So don't get obsessed with, oh, these are the invariant points, right? It depends on what we're doing. The location of those points depends on the type of transformation. You have to think about what are we doing to the points, right? So when we did inverse relations, the invariant points were where y equaled x, because what we do for the inverse is swap the y and the x coordinates, right? Well, that's going to be different if we do a different type of transformation, right? In a stretch or reflection, a vertical stretch or reflection, y values are all multiplied by a. So to figure out what our invariant points are got to be, we have to think about what type of number doesn't change when you multiply it by a. And there's only one answer, and that is 0. Invariant points only occur where the original y value was 0. Because the only number that you can multiply by any a, and it not change is 0. 0 times anything is still 0. So no matter what a is, a y value of 0 will be unchanged when we multiply by that a, which is all we do in a vertical stretch or reflection. Multiply the y values by a. So since y equals 0 is on the x-axis, or is the x-axis, sorry, we therefore know that any vertical stretch or reflection is just going to have invariant points where the original graph crosses the x-axis, right? In other words, it's x-intercepts. So, pretty quick example here, each of the graphs below is going to be vertically reflected across the x-axis. Identify the location of any invariant points if they exist. Well, do you see anywhere that wouldn't change if we multiplied every y value by a, right? Here we go, by negative 1, I guess, if it's vertically reflected. What about there, right? Invariant. Because if I multiply that y value by a, negative 1 in this case, it's still going to be at 0. The y value is 0 there. Can't quite tell what x is, but y is 0. Anything times 0, including negative 1 times 0, is still 0. So that point will not move, right? The reflection will end up looking something like that. That point will still be there. What about this one? Does that have invariant points? No, it doesn't, right? Because y is not 0 anywhere here, right? Y is just some number. It's 5 or larger is what we can see. So, 5 times negative 1, that changes it. It becomes negative 5, right? 6 times negative 1, that changes it. It becomes negative 6. There is no y value on this graph that is not going to be changed if we multiply it by negative 1. The only number that we can multiply by negative 1 and not change is 0. So this does not have any invariant points. Nowhere on that graph is y equal to 0. So everywhere will change when multiplied by negative 1. Last one here. Does this have invariant points? You betcha. Count them up. How many do you see? I see 1. Y is 0 there. 2. Y is also 0 there. 3. Y is also 0 there. Right? 3 invariant points. So this one will look kind of cool when we reflect it in the x-axis, right? This is going, up to positive infinity here. It's going to go down to negative infinity. This will do a bloop, and a bloop. Okay, I'll get rid of that because it's crowded. But those points will be unchanged because anything times 0 is still 0. All right. So go ahead and give this one a shot. Wants you to sketch the reflection of that original function f of x, and then whatever other practice questions you have to do or need to work through to feel comfortable with the material, you're free to go do that now, of course. And don't forget to reach out with any questions, concerns, book a meeting with me if necessary. I'm happy to help. There we go, lesson 4 done.